That's going. Welcome back. You're prudent to be here. I thought I would do a little bit of a quickie sort of review of how the test went in general. The bonus essays that are on the back side of the exams have to be read and graded by hand, obviously. Those are being graded not as we speak, but because Eli's right here. But they are being graded. I know that some of them have been, some more will be. Those grades will be posted when they're done, and they'll be posted separately. They will not simply be added into the hour exams. And there's no point in asking us when they'll be posted, because we'll post them as soon as they're done. If you have a question about your Scantron sheet, after the bonus questions are posted, the Scantron sheets will be available for people who want to look at them, but we're going to keep them all together until then. There are 4 people who somehow or other managed to slip past our attempts to make you double-check your answer sheets who did not code in your form. And we made our best guess at giving you the sheet that would give you the more points, which one it probably is, but we haven't finished grading those by hand. Those will be graded by hand after the essay is graded. So if you see a 0 on icon right now, it probably means you forgot to put in your form. And you will get a number there after the essays are done. Sorry about that. Overall, the performance was reasonably strong, especially for the first course in the test in the course. About 25% of people had 90 or above. There were 4 people who had 101 points. About a third of the class got between 80 and 90, and another 23% got above 70. I have concerns about the people who are below 70, and I'll address those in a little bit. There were a couple of questions that people seem to ask a lot of questions about, so I'll discuss a little bit how we use the question statistics and how we make some of those decisions. The exam service tells us for every individual question 2 numbers, one called the difficulty, how hard it was, what percentage of people got it right or wrong, and something called the discrimination. And one way of thinking about this number is how good or fair a question is it? Do people who know the rest of the material on the test usually get this one right? And so the discrimination is a number that helps me judge in a more objective way whether the question was fair or well written and so on. So for example, if there is in fact a better answer to a question than I think is the best answer, the discrimination will usually show up as that answer having a positive number because the people who know the rest of the test are putting that one down instead of the one that I expected to get. So the discrimination is a number that helps me sort of stand back and say, was this a fair question or a good question? I'll also remind you that I asked you to put down the best answer, not simply the correct answer. And there are a couple of questions where you can make a case that one answer is sort of correct, but I will explain why I think the one that was posted as the best answer was the best answer. Several people were concerned about the idea that prokaryotes have internal membranes, and I went to a considerable length to distinguish myself from the book by pointing out that prokaryotes have internal membranes. This is one of the slides in the... Sorry about that. I'm very embarrassed about that. Excuse me. Ignore it. Let's see. There we go. I almost never get phone calls. It just completely shocked me. It's true, you know. So I also noted specifically about the fact that prokaryotes can be multicellular, can be differentiated in terms of all those things. I hope that just as a reminder that if I go to the trouble to contradict the textbook, there's a reason that I went to the trouble to do that. This is another figure that I had in the handouts showing you the smallest eukaryote and a fairly typical blue-green alga or cyanobacterium showing you both its good size and it has all those internal membranes. So I'm not going to yield on that one. The ethanol dimethyl ether question was one of the hardest questions on the test. The difficulty shows us that. But the discrimination also shows that it was, in fact, a fair one. That is, that students who got most of the other questions right could get that question right and were not confused into answering something else. Looking at the structure of these 2 molecules, they both have oxygen atoms. And in the ethanol, you have the oxygen atom with a hydrogen off of it, whereas in the dimethyl ether, you have the oxygen atom with 2 methyl groups off of it. And these oxygen atoms, can each of them be a hydrogen bond acceptor? The hydrogen can be a hydrogen bond donor. And because ethanol has both donor and acceptor atoms in the molecule, it can make multiple bonds to itself, and that's why it has the higher boiling point. The idea here was to think about what we talked about water and the fact that water makes hydrogen bonds both as a donor and acceptor, and that's why it had such an anomalously high boiling point. So this question combined whether you in fact had reviewed those functional groups, whether you could combine that knowledge with what we had discussed about the structure of water. And I just have a little quote here from Wikipedia. One of the questions that I got by email was that my chemistry professor told me that ethers never make hydrogen bonds. And I'm going, I don't think he said that. So I sort of here offer you this from Wikipedia, that ether molecules cannot form hydrogen bonds among each other, but they certainly can form hydrogen bonds because they are hydrogen bond acceptors, not donors. So whereas the first foil on that is sort of true, the one I give as the correct answer is a better answer because it's more detailed about why hydrogen bonds are forming or not, and in fact is more generally true. That is, it's true under all conditions, whereas ethers don't make hydrogen bonds only in pure masses of ether or in the absence of other things like that, whereas they do make hydrogen bonds at other times. So I'm sticking with that one. I do recognize it was one of the harder questions. I mentioned at the beginning of this that I am a bit concerned that there are some students who got less than 70 points on this test. The course is not going to get easier from this point. It's going to have more and more new material. It's going to build on the material you've had so far. So someone who is below 70 at this point should be stopping to ask themselves what they want to do next about the course. Do they want to develop different study strategies, or do they want to focus their efforts on their other courses and not go ahead with this one? I have always, and will continue, to invite everybody, even if you've got 101, to come and talk with me or with the TAs about study strategies and how to learn more biochemistry. I'm always delighted to discuss that and help you personalize your study strategies. This is the first year I want to try something a little different, which is to further incentivize people to do this. If you got less than 70 on this test, not merely do I invite you to come talk to me or to Eli, but if you actually do come and talk to me and Eli before next Wednesday, I will give you up to 5 bonus points for having taken that step so that we can help you do better in the course. So you can get you can bring your grade up to a 70 through these bonus points. This can't hurt anybody. This is not a curved course. No one is going to have a worse grade because of my offering this. I'm just hoping that this may register with people who got less than 70, that now is the time to act, not after the second test, not after the third test. So if you're not happy with how you're doing, we really want to help you do better. Let us help you. I hope that's clear. I think that's the last of that. Okay. Any other questions about the exam that you wanted to ask me? Okay. We're going to move on then to talk about actual biochemistry as opposed to tests. And we're going to talk some more about enzymes. And what we've talked about so far about enzymes has been mechanisms, specificity, how an enzyme goes about lowering the energy of the transition state so it can accelerate reactions. And what we want to talk about in this chapter is a somewhat more quantitative approach to it, not a lot more quantitative, but looking at it trying to measure those properties and compare them to each other and how we can understand it, not just how an enzyme works, but how fast it goes. And enzyme kinetics gives us tools to describe both the speed of the reactions and to describe the specificity of the reactions. So enzyme kinetics gives us hints of both of those things, and I'm going to try to emphasize that those are separate aspects of an enzyme. And enzyme kinetics is important because it affects function. We're going to see as we get into metabolism how the specific kinetics of different enzymes is key to how those enzymes, in fact, contribute to their metabolic pathways. And having looked at these things in sort of the pure case, then we're going to look at inhibitors, that enzymes can be interfered with in one way or another, and that by looking at the kinetics, we can talk about competitors that are competitive or uncompetitive or non-competitive, mixed versions of all that. And finally, how those inhibitors and so forth give us some analogs to think about allosteric regulation. Allosteric regulation is going to turn out to be at the core of a number of important pathways, and these enzymes that undergo allosteric regulation are almost like little molecular computers. Some of them take inputs from 4 or 6 different sources and then come up with an answer of, oh, well, then I should be doing this right now, you know? So it really can be quite amazing. Some enzymes catalyze really simple reactions that we can consider A going to B. So you start with one thing, you end with a different thing. The particular example they're showing you here, triose phosphate isomerase, is one of the enzymes that we'll look at in more detail when we get to glycolysis. It's worth learning these guys now or then. It's up to you which of the two you want to do. And all that it does is it takes this molecule, glyceraldehyde, so this glycer rate tells us the 3 carbons. Glyceraldehyde is an aldehyde group here. Glyceraldehyde 3-phosphate. So this enzyme is going to take glyceraldehyde 3-phosphate and isomerize it, rearrange it, into dihydroxyacetone phosphate. So acetone is, of course, has a carbonyl carbon there in the middle. Dihydroxyacetone would have had a hydroxyl group here and here, but this one has a phosphate on one of the 2 hydroxyls. So it's an isomerase reaction. We haven't gained or lost any atoms. We just moved them around a little bit. When we get to glycolysis, we'll see why it's a really good little enzyme. But it's about as simple reactions we can do to think about kinetics. So A is going to go to B. And if we just simply looked at A and B as a function of time, we start off with some pure glyceraldehyde 3-phosphate as the substrate. We add a little bit of enzyme. We can watch, and what we're going to see is that the substrate is going to disappear over time as the product, dihydroxyacetone, appears. And we talk about velocity, or V, is the rate at which either the product appears or the substrate disappears. It's a rate. It's a change in concentration over time. So the velocity of a reaction is how fast the product is appearing, how fast the substrate is disappearing. And so we can look at this in a little bit of simple mathematics again, that if A goes to B, we can say mathematically that the velocity of that reaction is the change in the concentration of A with a function of time, or there's a rate constant times the concentration of A. So that's the simplest kind of kinetic equation we can have. If we have 2 reactants, the math starts to get a little bit more interesting. So let's say we have A plus B are going to go to C. Then you have a velocity is going to be the disappearance. There's a negative sign here. There's one there too if you take a close look. The disappearance of the decreasing concentration of A with time, or the decreasing concentration of B in time. But the rate constant in this case is going to be dependent on the concentrations of both A and B. So it's going to be more complex because it's going to depend on 2 things now instead of on 1. If we want to take a simple case, and we start out with a situation where we have the substrate S in excess, there's a great deal more substrate than there is enzyme. Then when we increase the concentration of the enzyme, we're going to increase the velocity, the reaction velocity, the V. So when there's all the substrate in the world possible, more enzyme goes to a faster reaction. So that's one of the things that's saying that it's the enzyme that's increasing the rate of reaction. If, by contrast, we hold that concentration of the enzyme constant, and now look at how the enzyme reaction, the reaction rate goes as we change the substrate concentration, we get a little bit of a different graph. So here we're going to have a constant enzyme, and we're going to start with a substrate from 0 on up. We're going to increase the substrate concentration. And what we see when we do that is that initially we see the reaction going. You're increasing the amount of substrate. The rate of the reaction is greater, but it doesn't increase indefinitely. It starts to taper off. Okay, that kind of tapering off curve should look familiar to you. It looks rather like the curve for myoglobin and oxygen binding. It's a hyperbolic curve. And this tapering off with higher concentrations. So, here is the rate of the reaction is here. We double it. We haven't come anything like close to doubling the rate because the enzyme is starting to get saturated with the substrate. And so it's going to approach a maximal velocity of some kind. And this kind of experiments and others like it led to early analyses of enzyme kinetics that reflected on it as being sort of a several-step process. You have enzyme plus substrate. They bind together to make an enzyme-substrate complex, and then something magic happens, and they break apart into enzyme and product. And we're going to see that conceptualizing enzyme kinetics like this is going to be a fairly powerful tool. But again, you can see that this curve, this simplest of enzyme reaction curves, where we're looking at velocity of the reaction with enzyme substrate concentrations increasing, very similar to the myoglobin hyperbolic curve. So thinking of this enzyme process as having enzyme and substrate going to make an enzyme-substrate complex, which can go forward at some rate to enzyme and product, lets us break down the little micro steps here with a couple of different rate constants. So the mixture of enzyme and substrate as free things going forward to make enzyme-substrate complex has a forward rate constant called K1. This enzyme-substrate complex can fall apart and just go back to being enzyme and substrate. That's what we call the back reaction, or K minus 1. Or it can go forward to make enzyme and product, and that's K2, the second forward rate constant. So if we start off with a mixture of substrate and enzyme, just pure substrate and pure enzyme, and mix those two things together, we can see that there's a transition while the reaction gets started going, and then we get to what's called a steady state. So if we initially mix at time 0, some enzyme and some substrate, you won't instantly see the full disappearance of the substrate because you have to form some of those enzyme-substrate complexes. So you're going to have a decrease in free enzyme as you get an increase of enzyme-substrate complexes. And as you start to have more of the enzyme-substrate complexes, you're going to have more around in order to make product. So after a little bit of a lag, you start to see product being made. And if you look here in the middle part of this graph, sort of roughly like this, what you see is there's a constant amount of enzyme, free enzyme, that's recently let go of everybody. You have a constant amount of enzyme-substrate complex. You have an increasing amount of product that's increasing linearly, and a decreasing amount of substrate that's decreasing linearly. And this range in here is something that we call steady state. Things are going in and going out at a balanced rate. It's not an equilibrium. It's a steady state. It's like water passing through a pipe. That water's not at equilibrium, but it's entering at one end and going out at the other end at a constant rate. So this is a steady state for that enzyme complex. Questions? Okay. So if we looked at this previous equation and do a little bit of rearranging, we can say that the velocity of a reaction, or the appearance, the rate at which the product is appearing over time, is K2, that forward constant from the concentration of the enzyme-substrate complex. So the rate at which the product will appear is the concentration of the enzyme-substrate complex, and that forward rate constant in when the reaction actually happens and you go to product. And if we do some rearranging with this, we can say that there's a change in the enzyme-substrate complex over time that can be described as being the forward rate constant and the free enzyme and substrate. You're losing enzyme-substrate complex by the back reaction by K1, and you're losing enzyme-substrate complex by K2, that forward reaction to making enzyme and product. So this is the rate at which the enzyme substrate complex would change over time, which is a kind of a messy equation. And so, like sneaky biochemists and sneaky scientists from the beginning of time, we pick conditions where it's not as messy. And if we pick conditions where the amount of substrate that's available is much, much greater than the amount of free enzyme, then under those conditions, the change in the enzyme substrate complex over time is zero. That's the steady state we were talking about in the previous graph. And so by picking carefully our conditions, we can find a condition under which this can be treated as a constant, and then that will allow us to progress with the rest of the mathematics. I once saw Robert Mays, the ecologist, who pointed at a big ecology equation and said, well, that's too hard to solve. So here it says log x, we'll just call that 1, because with an order of magnitude, the log of any number is 1. It's like, what? It actually worked, too. I'm not going to do the rest of the derivation. I know that some of you folks are very mathematically inclined, and you will find it useful. It's in the book. For others of you, it will simply make you feel more lost than before. So instead, what I'm going to do is go straight to something called the Michaelis constant. The Michaelis constant can be defined as a composition or putting together into one term these different rate constants of the forward and back reactions. So the Michaelis constant is a ratio of the things that break down the enzyme substrate complex. K-1 is the back reaction back to enzyme and substrate. K2 is the forward reaction that makes enzyme and product, over K1, which is the reaction that makes enzyme substrate complex. So Michaelis constant is a single number that puts all of those into a single number. And what's interesting is that having the Michaelis constant now allows us to relate different properties of an enzyme reaction. So this equation here is called the Michaelis-Menten equation. Leonore Michaelis and Maud Menten are responsible for this, the early part of the 20th century. So the velocity of a reaction is going to depend on several things. It's going to depend inversely on this Michaelis constant, the tendency for the enzyme substrate complex to form or not. It's going to depend on something called Vmax, the maximum velocity that this reaction can attain when fully saturated. And it's going to depend on the actual concentrations of the substrate available. So the velocity at a given instant is going to be an overall outcome of 3 different numbers. The concentration of substrate is something that is a variable. That can vary for either laboratory reasons or physiological reasons. But the Vmax and the Km are both of them properties of the enzyme itself. And so this brings us to another hyperbolic curve. And here we have substrate. We're increasing substrate, and the velocity is rising. So this is similar to the graph we saw earlier. You can see that as we start to add higher concentrations of substrate, the velocity of the reaction starts to rise, and then it tapers off so that going from here out to here, we don't come close to doubling the velocity of the reaction. Now, trying to look at the maximum velocity, you can see it's tapering off here. One of the problems with hyperbolic relations is this thing tapers, off to infinity, on to infinity, and beyond, to quote what's his name. So Vmax is a tricky thing to use as a observable. So instead what we talk about is a Km is equal to the half maximal velocity. So you can see here that if the concentration of substrate is equal to the concentration that gives you a half maximal velocity, that concentration is equal to the Km. Okay. So the Michaelis constant is it's in the units of concentration. It's going to depend both on how good an enzyme is at selecting the substrate and how good it is in converting that into the product. It's approximately the same thing as thinking about the affinity of the enzyme. It's how tightly it can hold on to something. And it's more like an affinity when the forward reaction of making a product is a lot smaller than the backwards reaction of letting go. And that's true for a lot of enzymes. So we have a number here that allows us to talk about the affinity of an enzyme for its substrate. And again, in approximate terms, this is approximately what the Km will be equal to the free enzyme and substrate over the product, over the complex, excuse me. All right. Another enzyme property that we can talk about is the K-cat. And this is measured by looking at the Vmax over the total enzyme concentration. So Vmax is going to tell you how quickly the reaction goes in the forward direction when the enzyme is saturated, when there's no limitation for getting a hold of the substrate. There's substrate there, all the time. It's how fast it goes forward to make a product when it's occupied. The units for K-cat are per second, so it's reactions per second. It sometimes is also called the turnover number. And so now we have one number, the Michaelis constant, the Km, that is a measure more or less of affinity, how good it is at holding on to a substrate, and another number, the K-cat, that's a measure of how fast it makes a product when it's occupied. And the ratio between those two allows us to have a single number that gives us a single number comparison to compare different enzymes to each other. So the ratio of K-cat, the turnover number, over the Km, roughly speaking, the affinity, is called catalytic efficiency. When you've got it, what do you do with it? I really want to emphasize that K-cat, the catalytic number, and the catalytic constant, and Km, the Michaelis constant, are completely independent numbers. If you know the Km, you don't know what the Vmax is. If you know what the Vmax is, you don't know what the Km is. Affinity and Vmax are completely separate properties. One has to do with whether or not it can bind the substrate, and the other has to do with, now that it's occupied, how fast does it make product? Separate, distinct, independent properties. They're different. They're independent. Can anybody think of another way I can say this? If I seem like I'm making a big deal out of it, it's because apparently this is a hard thing to grasp, and this year I'm hoping I can get everybody on board with it. One of the things that comes out of catalytic efficiency in studies like this is you can look at what properties limit an enzyme reaction. And there are some enzymes that are only limited by diffusion, by how fast the new molecule is diffusing to the enzyme, and a few that are faster than diffusion. Superoxide dismutase has one of those tractor beams I was talking about where it has a little electrostatic field and it can suck in its substrate. So, kind of cool. All right. So we have these numbers, Km, more or less speaking, affinity, the tendency to hold on to something, half saturated, when you're half saturated, that's the Km, or Vmax, how fast it goes forward when it's occupied. If we use that hyperbolic curve, that's a graphical representation of it, and it's not a very precise way of going about it. And a number of different approaches have been taken to trying to get a handle on enzyme kinetics and how to do that quantitatively. There are transformations by which we can take our previous equations and turn them into linear equations. And linear equations are easier to graph and easier to work with than nonlinear ones. So we started with this. This is the Michaelis-Menten equation. The actual velocity at this instant is going to depend on the Vmax, the forward rate when it's occupied, times the actual substrate concentration, over the Michaelis constant, it's a tendency to be able to hold on to the thing, plus the substrate concentration. If we do this as what's called a double reciprocal, And so if we look at 1 over the velocity, so down here we've turned this into 1 over the velocity, we can rearrange that equation into this form. Km is now on the top, Vmax is now on the bottom, times 1 over the substrate plus 1 over Vmax. If folks want to go through that transformation with me sometime, I'm happy to do that, but for the moment, take my word, that's the Lineweaver-Burke equation. Oh, this was supposed to have been fixed. I'm sorry about that. Funny. There's no E on the Burke. Scratch the E off. That's funny. I know. We asked her, didn't we? Oh, well. It's fixed on that copy? Oh, okay. Well, now I know. Okay, I think I know what happened. Okay, great. Anyhow, good. It's fixed on your copies. That's good. Look at this equation, and you'll see in it this simpler-looking equation, y equals mx plus b, which you may remember from 9th grade math is the equation for a straight line. So odd-looking as this equation is, it is nonetheless an equation for a straight line. And what would it look like if we were to graph that? It would look something like this. So remember, this is the Lineweaver-Burke equation here. Y equals, there's your m, that's a constant, mx plus b, that's your second constant. So when you do what's called a double reciprocal plot, so this is 1 over velocity instead of velocity, this is 1 over substrate instead of substrate, you can get a straight line out of it. These are the actual data points here. So this data point out here is actually at a very small concentration of substrate and a very low velocity. And as we add more and more substrate, 1 over s gets bigger, and so does the velocity. So this is the highest velocity that we actually measured. But because this puts those hyperbolic points now on a straight line, that straight line intersects both the y-axis and the x-axis. And the place where that line intersects the y-axis is 1 over Vmax. It's the reciprocal of Vmax. And if you continue that line past the actual data points, but let it keep on being straight, you now are in the negative domain of the x-axis, and this is minus 1 over the Km. And that just comes out of the transformation of the equation. So this allows us to get a number for both of these very important kinetic properties, the Vmax and the Km. I hope it also brings home that they're different numbers. One of them's on the y-axis and one of them's on the x-axis. One of them has units of velocity and one of them has units of concentration. It also can make it easier to make comparisons. And when we do some of the inhibitor comparisons, I think the advantages of Lineweaver-Burke will become more obvious too. Okay. So far we've been talking about like a real simple equation of A goes to B. And there are certainly equations that are that simple, reactions that are that simple. Triose phosphate isomerase is an important enzyme, and we're going to see others. But in blunt reality, not very many are quite that simple. Most of them involve more than one substrate or more than one product, or maybe more than one substrate and more than one product. And this is just giving you one example of the kind of thing that we're going to see multiple times as we get into metabolism, that you have substrate X that's an oxidized compound and Y that's a reduced compound, and this wonderful enzyme does stuff to it, and now X is reduced and Y is oxidized. You know, that kind of redox reaction is going to play a big role in a lot of things. And this is just showing you a number of different, this is another example of a two-component reaction. This is not a redox reaction. This is an enzyme called transketolase. And we're going to see this enzyme again later on. This is fructose 6-phosphate, a very important phosphorylated sugar, and glyceraldehyde 3-phosphate. We already saw that one. And transketolase is going to pull the cute trick of taking these 2 carbons and smooching it on top of there. So it's going to go from this 6-carbon sugar and this 3-carbon sugar to a 4-carbon and a 5-carbon sugar. Now, it's going to bind fructose 6-phosphate and it's going to bind glyceraldehyde 3-phosphate. Transketolase has 2, count them 2, Kms. It has to have a separate Km for each substrate. So it's going to have an affinity for fructose 6-phosphate. It's going to have an affinity for glyceraldehyde 3-phosphate. And there's nothing that says those have to be the same. And often they are different. Okay? And if you stop to think, what this looks like in detailed kinetic terms, this is breaking that reaction down into all the possible, micro constants. So you have fructose 6-phosphate and the enzyme transketolase. Those two can bind to each other to make an enzyme substrate complex of the two of them, which would be that forward arrow, or they can fall back apart into the two individual things. This enzyme complex can go forward to the 2 and 4 fragment form, or go back to this one. If you have the 4 and 2 form, you can have the 4 carbon fragment come off as erythrose 4-phosphate, and have simply the 2 carbons left bound to it, or that can go back. This one can go forward by binding a glycerol 3-phosphate, or go back. This one can go forward to this, or go back. And then that can go forward to the 5 carbon and the enzyme xylose 5-phosphate, and so on. So each one of those arrows is a rate constant. I am not going to ask you to try to think about that many rate constants. However, despite the fact that there are so many micro constants to this overall thing, you can still talk about a K-cat getting from fructose 6-phosphate to xylose 5-phosphate. There's an overall determining catalytic rate. That may be entirely attributable to one particular step, or it might be kind of a combination of a couple of steps, but you can still think conceptually about the rate at which fructose 6-phosphate gets to xylose 5-phosphate, even if you don't want to think about all the little steps in between. So far we've been talking about hyperbolic reactions, the simple kinds of reactions. Hyperbolic reactions obey Michaelis-Menten kinetics. Some enzymes don't look like that. And so this is an example of something that has sigmoid kinetics, where again we're starting off with no substrate. We're going to raise the substrate concentration, and the velocity is going to start to rise, but maybe not as fast as it did initially for the triose phosphate isomerase. And then it hits sort of a semi-linear part and then tapers off again. This should remind you of a sigmoid curve. The sigmoid curve probably would trigger in your minds hemoglobin, which had sigmoid oxygen binding. And in fact, when an enzyme has sigmoid kinetics like this, it typically, almost always, means there's some kind of cooperative behavior going on. Some kind of allosteric behavior where something is interacting with the enzyme to change its kinetics as a function of substrate concentration or something else. We can still speak meaningfully about a Km and a Vmax. The Km is still the concentration of substrate that will half saturate that enzyme, so it's a measure of affinity. And the Vmax was still that ideal top velocity at which things go, so it's a measure of how well it goes forward when it's occupied. So they have the same general kinds of meanings, but they have to be measured in different ways than when you have simple hyperbolic kinetics. Any questions? Okay. All right. So far we've been talking about enzymes doing their thing in the unrestricted state, without interference of any kind. One of the major tools for thinking about enzymes, as we've already seen when we were talking about enzyme mechanisms, is using inhibitors of different kinds. That inhibitors can step into that reaction and modify it in some way, and as a result be sort of a tool for dissecting it. They're not exactly the easiest tool sometimes. My mentor at MIT said only the uninhibited use inhibitors, but they are nonetheless can be powerful tools. One kind of enzyme inhibitor that has been very powerful is an irreversible inhibitor. And in the case of irreversible inhibitors, typically speaking, these are things that are substrate analogs. They look kind of like the actual substrate, so they can bind at the active site, but they have on them a reactive group. And that reactive group can then become covalently attached to the enzyme and irreversibly sit in the active site and exclude anything else from getting into that active site. The reactivity is typically at the active sites. Sometimes it's elsewhere. These are also sometimes called suicide substrates. And this is just sort of showing you a little diagram of that. Here's a chymotrypsin Pac-Man. We talked about DIPF was one of the inhibitors that was used to analyze the catalytic triad. And this will fit into the active site, and it tries to cleave it. And in the process, the fluoride is released, and you now have DIP, diisopropyl chymotrypsin. So it's occupied there. It's covalently in there, and it won't ever come off again. Interestingly, one of the most powerful reflux medicines, omeprazole, also called Nexium and a few other things, is an irreversible inhibitor of the proton pumps. Basically, once it's reacted with that proton pump has to be replaced before there's a functional pump back there. Here's another example of a suicide substrate. This molecule is 5-fluorouracil. So here's a fluoro group that it's otherwise chemically similar to uracil. And so here you have one of the important reactions necessary to making more DNA molecules. You want to make DTMP, thymidylate monophosphate, because it's thymine that's in DNA, not uracil. And so you have to make that out of deoxy-UMP. This is uracil monophosphate. So thymidylate synthase is going to add this methyl group at the 5 position. But 5-fluorouracil, you can see, is in a position where it can poison that enzyme quite powerfully. And since cancer cells typically, although not always, grow more quickly than the other cells, the normal cells, things that inhibit DNA synthesis preferentially affect cancer, not exclusively, or people's hair wouldn't fall out, but they preferentially target the cancer cells. So that's irreversible inhibition. It comes and it never checks out. There are a number of other ways that inhibitors can act, but to do so reversibly. One common form of reversible inhibition is called competitive inhibition. For it to be actual competitive inhibition, it has to be completely reversible. And this is certainly a common kind of inhibition that we see. So we still have our Pac-Man enzyme here again, and the substrate that would fit into an active site like that has to have the right shape to fit it. And the inhibitor in this case has a shape that is such that it can fit in at that active site. It in some way mimics the right binding at that active site. So it has a similar structure, but it's not reactive. It's not going to produce product. And so what do enzyme kinetics look like in the presence of an inhibitor? Here in the green line, sorry about that, guys who may be red-green colorblind, in the upper line, which is the green line here, this is the enzyme kinetics in the absence of an inhibitor. This is its normal, natural kinetics. So as we add more substrate, the velocity is going to rise, then it's going to taper. We're going to be able to have a measurable Km at the half maximal concentration. So half maximal velocity is the Km, and then there's some maximal velocity that it approaches. In the presence of a competitive inhibitor, that competitive inhibitor can bind at the active site some of the time, and then the rest of the time it'll be the substrate that binds at the active site. So if you have a constant amount of inhibitor present, you have a fixed amount of inhibitor present, if you keep adding more true substrate, more and more often, it'll be substrate that's there instead of inhibitor. So as you increase the concentration of substrate, you can overcome the inhibition. And what we see with true competitive inhibitors is that they can recover the same final maximum velocity in principle, if it's all soluble enough, but it changes the apparent Km. That is, it takes more substrate to get it to the half maximal velocity. So a competitive inhibitor appears to change the Km, the concentration it takes to half saturate it. But it does not affect the maximal velocity, because when you have quasi-infinite amounts of substrate compared to the inhibitor, then you get the reaction going with its normal forward direction. The odds of it being a substrate molecule sitting down are much, much higher than of an inhibitor molecule sitting there. So Vmax and Kcat are both unaffected by a competitive inhibitor. And now we see why the Lineweaver-Burke plot was kind of a nice thing to take advantage of. This is something that makes it a little bit easier to see how this plays out. So here again, the green line, sorry about that, guys, is the kinetic behavior in the absence of the inhibitor. So the data points would be sort of sprinkled along in here somewhere. The y-intercept on the 1 over velocity is 1 over the Vmax, and the x-intercept on the substrate x-axis is -1 over the Km. So here's your measure of affinity. Here's your measure of how fast you go when you're saturated. And in the case of a true competitive inhibitor, that's just a competitive inhibitor, you'll see a change in the slope. The Vmax will be unaffected, and you have a change in the apparent Km. Because this is a reciprocal plot, moving that -1 over Km to here is saying it has apparently weaker affinity. It takes more substrate to get it to go to the half maximal rate. Okay? And you can see they're using these little alpha terms to modify the uninhibited kinetic parameters. And I think that's probably a good place to take a break. So I'll see you all Friday. Remember my offer. If you have under a 70, either meet with me or Eli, and we will help you strategize. And anybody is invited to do that. AV person, we're done. AV person?